Hey everybody. In this video, I just want to show you how the center of mass of a system of two objects will follow Newton's first law, and that center of mass will continue to move at a constant velocity um, before and after a collision or an explosion or any interaction in an isolated system. So just a really quick review of an actual case here. What we're going to do is set up two masses, 1 and 2. You can see that mass number 1 has a velocity of 2 meters per second, and mass number 2 has a velocity of 0. And I can show that with the velocity vectors. So we're going to have a collision here. Mass number 1 is going to move. It's going to hit mass number 2, and then we're going to make them stick afterwards. Okay. The actual masses of those objects are 1 kg and 1 kg. You can see that at the bottom of the screen. I'm going to turn off the velocity vector, and as you can see, I have turned down the center of mass. So you can see the center of mass is right in the middle of the two objects, which you'd expect because they have equal masses. So let's just do a quick run on this. Keep your eye on the center of mass. That is the X in the middle. You can see it's moving at 1 meter per second. And after the collision, the center of mass continues to move at 1 meter per second. Okay, so that was kind of the animation. Now we're going to go back to the packet, and give me a moment here. All right, I'd like to show you this exact same case, but this time we are going to make a diagram. And so you'll notice here that we have a 1 kg mass and another 1 kg mass. And the initial velocity of the first one, the circle, is 2 meters per second. The initial velocity of the second one is 0 meters per second. Now, what you are going to be doing in this packet is you're going to sketch the position of the center of mass, and you're going to show how that moves. And then after the collision, you're going to show that it continues to follow the same path. Okay. So in this packet, what we're doing here is we're kind of like saying that each one of these lines, the rows, is a time step. So you have 0 seconds, and then 1 second, and then 2 seconds. And I'm gonna label it all the way down. And then where it says stop here, that's going to be 7 seconds. So you're going to make a diagram, like a motion diagram, kind of like a dot diagram of these colliding objects. And you're going to show the center of mass position. Okay. So first of all, let's map out what happens up until the collision. And so what we're going to do here is we're going to make each one of these blocks 1 meter. And so if you look at this first mass, it moves at 2 meters per second. And so that's why you're taking that circle and you're making it move up by 2 blocks, all right, after 1 second. So I'm going to continue that with the circle. So another second goes by, and now it goes there, and now it goes here, and eventually it goes here. So we're making that move 2 meters, right, every 1 second. Now, the square, of course, doesn't move at all, at least not initially. And so that one just kind of copies down. And of course, when they're in the same place, at 4 seconds, that's where they have the actual collision. Okay. So let's go ahead and find the center of mass position of these two objects. Now I'm going to move to red, change this to red. And again, remember that the objects have equal masses. And so I hope it's pretty obvious to you that if masses, then the center of mass is going to be right in the middle. So what do we have here for the first 0 second? We have 1, 2, 3, 4, 5, 6, 7. We have 8 spaces in between them, 8 meters. So that means that the center of mass is going to be right in the middle. It'll be 4 meters away from the first one. Now, you can follow that same logic, and you can say in the next case, you've got what? 1, 2, 3, 4, 5, 6. And so you'd be 3. The center of mass would be in the middle again, which is 3 meters away from the circle. And so you just keep going down the line. Now, this is pretty easy, right? Because you just mark the center of mass in the midpoint. And of course, when you get to the collision, it's down here. Now, just a word about this. What would happen if the masses were not equal? Well, then the center of mass would move closer to the larger mass. You'd have to probably do a little bit of math on the side. So let me just illustrate maybe this example right here. I'll put an arrow here. And how would I predict that center of mass position that I have there using these numbers? And so a lot of times what I'd like to do is probably just to make the circle my origin. And remember in class, we used a formula for finding center of mass. And so I would do something like this. I would say that with this as my x is equal to 0, my center of mass is going to be equal to, and then what I do is I multiply the first mass times its position, and I add the second mass times its position. So this would be 1 kg times 0 meters plus, and then I go to the second mass, which is what, over here, right? And that would be 1 kg times 6. Why 6? Because remember, if I use this as my origin, I go 6 meters over to get to that. So mass times position plus mass times position, and then I divide by the total mass of 2. And of course, that's 0 plus 6, which is just 3, and these are meters. And that's why I know, see where that is? I know that's the center of mass right there. So anyway, sometimes you may have to do this in the packet. The masses, if they're not equal, you're probably going to have to do some calculation like that. Okay, so let's now take the path that the center of mass follows, and let's move it. Let's project it forwards and see where it goes. So I'm going to draw a line here. Let's see, in Cami with my shapes. I'm going to make this kind of bold. I'm going to make it green. And I'm going to start off with my first point, and I'm going to continue and draw this green line, and I'm going to extend it all the way down to the bottom here. Something like that. And what that green line shows is that's the path that the center of mass would follow. Okay? And so it's actually making some predictions for us. What that path is suggesting, as we saw in the simulation, is that we expect the center of mass to be here, and then here, and then here, and then here. And so I just want you to believe that and to see it. So I think what we need to do is we need to show that after these two objects collide and stick, that they're actually going to be ending up in those positions, right? And I hope that you're pretty comfortable doing that, because that's a pretty easy calculation to do. We're going to calculate the system momentum here. And so we do kind of a P initial is equal to P final. And I'm simply going to show, what do I have to show? I want to show that after they collide and stick, that the final velocity of the two is going to be 1 meter per second, because it would have to be in order to keep up with this pattern that I've been drawing. So maybe you can see that already. If not, let's just do the math here. So the initial momentum of our system would be 1 kilogram times 2 meters per second plus 1 kilogram times 0 meters per second. After they collide and stick, they have a mass of 2, and you multiply that times V final. And so this is going to be 2 plus 0 is equal to 2 V final. Of course, V final is equal to plus 1 meter per second. So we actually showed that. That's great. And again, what we're trying to show is that the center of mass position is the same before and after the collision. Not only the position is the same, but its movement is the same. Its velocity is the same. So this is an isolated system, right? It's an isolated system. We assume there are no outside forces. And so the velocity of the center of mass is unchanged. Okay, and that's basically what we're trying to show here. Okay, so Yeah. One other trick, and I didn't ask you to show this, but I'll just show it to you right now, is that you can find the momentum of the system. You can find the P system by taking the total mass of the objects, the mass of the system, and multiplying it by the velocity of the center of mass. And so just to show you this, so in this case, the mass of the system would be 1 plus 1, and the velocity of the center of mass we just figured out is 1 meter per second. And that means that the momentum of my system is plus 2 kgs meters per second. And the reason I point that out is because that number, plus 2, is also equal to that we calculated for the P initial, right? It's also equal to P final as well. So a different way of finding the momentum of the system is simply to add up the masses and multiply by the velocity of the center of mass. And that tells you the momentum. All right, so good luck, and you can continue on with this. I would highly recommend using different colors to indicate the things that you're trying to show. And we'll check in later on.